So today we have Patrick Walton, who's going to talk about opportunities to use small sats for scatterometry. And I'll let you take it away, Patrick.
All right. Thanks, Sarah. Just share my screen. And thank you for having me. I'm excited to share what we've been working on. So I'm Patrick Walton. I'm with CareWeather Technologies. So we spun out of Brigham Young University after studying with David Long. And I will be talking about hourly ocean surface vector winds from a constellation of small scatterometers. Most generally, scatterometry is measurement of surface scattering characteristics. In the realm of Earth observation, that's historically been done through satellite radar, which the scatterometer satellite radars are similar to synthetic aperture radars, SARs, but with more limited resolution and wider swaths. You're taking your power and spreading it across a wider swath. And the observables that you get from that include ocean surface vector winds, which will be our main focus today, but also soil moisture, vegetative water, and ice extent are some of the main ones. And this illustration from the QuickScat mission from NASA and JPL is a good illustration of those different parameters, both the wind, the vegetation over land, and the ice. So for winds with scatterometry, there's this requirement. If you're going to get wind vectors, wind speed and direction, there's this requirement for information diversity. And that can be done through varying geometries. It can be done through polarizations or frequencies. Most typically, the bulk of the information diversity is achieved through azimuth angle diversity. So that's either through multiple antennas, as with the fan beam scatterometer architecture, or with rotation. So there's the rotating pencil beam, which was the architecture that QuickScat used. And then there's a newer architecture that's been demonstrated by the Chinese called the rotating fan beam architecture. And today, the state of the art, really, at least in terms of data that's accessible to most stakeholders in the United States, is the ASCAT, Advanced Scatterometer, on the METOP satellites. And you can see some of the performance characteristics here. So over the 6 to 24 meter per second range of wind speeds, you get a maximum error of 2 meters per second and a maximum direction error of 20 degrees. And if you can tolerate somewhat larger errors, that data gets used from a somewhat larger range. And then the native resolution is 25 kilometers, but they have products that are processed down to 12. Typical latencies, 1 hour, refresh interval. And we'll talk about that a little bit more. The refresh interval, though, is quite large, and that's one major challenge. And then you get a pretty good swath with scatterometers, so 1,000-kilometer swath. So like I mentioned, one of the main challenges with scatterometry is there are not many of them, and so the refresh, the temporal sampling is somewhat poor. And, I only have scatterometers on here. There are other types of wind sensors, and I'll address that a little bit. When you add in a few others, it gets a little bit better, but still they have trade-offs, and the refresh for scatterometers by themselves, because the Chinese scatterometers are not available, is at a minimum 12 hours. But in reality, due to gaps in the coverage, you end up getting a worst case refresh closer to 26 hours. So I'll start a little bit by addressing some of the needs with scatterometry, though starting with science. I won't speak to them too much since our strength is in the technology, and so I'll address what we're pushing forward with the technology. But some of the main problems with science done using ocean surface vector winds, areas of science that are typically dependent on scatterometer measurements or other sources of ocean surface vector winds are the seasonal variation of the diurnal cycle in winds is something that's very difficult to observe currently with the diurnal cycle. Observing it requires at least 4 observations throughout the day at a minimum. But then when you look at sampling errors, in reality, your the conjunction of your speed error and your sampling go together, and there are some studies that, and I'll get to this in a minute, but there's some studies that suggest that at a 1 meter per second error, your with daily refresh, which is the best we have right now, your actual sampling due to Nyquist sampling errors is much longer than daily. So we're a long way. All that's to say, we're a long way from really observing the diurnal cycle well. And in addition, you look at scatterometers have typically been one of the better instruments for observing more of these synoptic air-sea systems, the mesoscale systems that cover hundreds of kilometers, and evolve on timescales on the hourly or even shorter. And so I've got a list of some of the examples of those here. All of these systems are currently really difficult to observe because you either have point measurements that have good temporal sampling, but very poor spatial coverage, or you have good spatial coverage, but it's only available very infrequently. So, and then from a decadal survey perspective, the scatterometers on their own provide a good supplement to the winds and currents targeted as observable, as well as there is some mention of ocean surface vector winds and need for increased sampling. And finally, from a general standpoint on the science, there is this need to secure the climate record and ensure that we don't have gaps. And currently, there's a number of instruments in the works that increase the chances that we won't have gaps. But the more we have, the more secure that record is. So, and I'm not an expert in air-sea flux, and I'm presenting to a number of experts, so I am a little bit on venturing into new ground here. But I did some research on and collected some of my notes I've taken over the years on relevance to air-sea flux, and what probably one of the biggest points is that among the variables that contribute to surface fluxes, wind has a very large range of frequency variability. So it's more volatile, and as a result, that means the need for more temporal sampling is outsized, especially when you start looking at extreme events that have a large impact or could have a large impact to flux. And so I found some other a paper talking about flux requirements, and they discussed a real ideal wind speed error of 0.5 meters per second. And when you combine that with what I was talking about before about the challenges with temporal observability due to Nyquist sampling errors, you can see that we're really far away from ideal refresh, from ideal temporal sampling, because with daily refresh, we're only the sampling errors really put us closer to 12 days, even at just 1 meter per second, let alone half a meter. So beyond the science needs, there are other needs that we've been talking to a lot of stakeholders. We're doing a National Science Foundation I-Corps program right now, which involves interviewing 100 people in 6 weeks. So it's been very interesting to learn from a large variety of stakeholders. We did a lot of interviews before this program as well. So some of the strongest ones that we've seen need are in maritime, especially for winds. And there's an interesting trend there where the International Maritime Organization is setting regulations for decarbonization of the shipping industry. And there's a variety of other regulations, especially local regulations, in terms of when you enter national waters, you're you have these requirements to reduce the run rate of your engines. And so a lot of the players, honestly, the bulk of the industry is really looking for ways to venture away from traditional fossil fuel propulsion methods. And they're exploring a variety of alternative energies. But one of the alternatives that is gaining a lot of traction is the idea of going back to wind shipping, in a sense. And so these ships typically don't have mast and sail systems that look similar to what you might be familiar with. They typically have somewhat more rigid or controllable systems that don't require quite the size of crew. But a great example here, one that's now operational, is the Canopy vessel that's used to transport the Ariane 6 rocket. So ESA's and Arianespace's new heavy launch vehicle. And so that vessel is equipped with these retractable sails that provide quite a bit of propulsion on the journey from Europe to French Guiana, where the launch site is. So, and then there are these other maritime sectors, fishing, sailing, where there's a need for situational awareness and also in sailing, especially a knowledge of the winds. And then, of course, energy, offshore energy. And then also, I'll add a side note. An area that we've started looking into is scatterometers have this capability for soil moisture, and we've been trying to understand the needs for water conservation, data for water conservation and water buyback programs, especially in the Western United States. Obviously, there's another area of large need is in government operations. So this is largely weather with numerical weather prediction and especially cyclones tracking and prediction. Also defense, there are very large assets with a significant risk if the forecast or if the identification of storms comes late and the lead time for evacuation warnings or warnings to secure assets comes late. And then, of course, search and rescue has this need to know with higher temporal sampling the conditions at sea in order to track maybe people who have gone overboard or similar issues. And this is a point of evidence that I for weather, but also I think is interesting side point of evidence for the role of winds and air-sea flux. But this was a study done by ECMWF on the forecast sensitivity of impact for a variety of observations, specifically for coupled ocean and atmosphere numerical weather prediction. And you can see on the left, the quantity of scatterometer data is very low, but then on the right, the impact per scatterometer measurement, very high, outsized even compared to other measurement types that have low quantity. So it makes it somewhat clear that there's a high return on investment possible for more scatterometer data in terms of benefits to numerical weather prediction, but also suggests part of that, this is especially specific to coupled numerical weather prediction in that scatterometers have a close tie to the air-sea flux that couples the ocean and atmosphere. So, we are focusing on scatterometers, but I mentioned there are a variety of methods for measuring wind from space, but they all have their benefits and limitations, which is part of why we decided to focus on scatterometers. That you have polarimetric radiometers, which are passive instruments. They measure the microwave emissions from the ocean surface, which are largely impacted by the surface roughness, which in turn can be correlated to the wind. I guess that's a key point that I forgot to mention earlier. That's how a scatterometer is measuring the wind, the surface roughness. There's a geophysical model function that correlates that surface roughness, especially as viewed from multiple directions, to the wind speed and direction. And so there's a similar model function for radiometry for those microwave emissions. And a classic, or a recent example rather, of wind vector radiometers is the CoVer instrument, which is currently operating on the International Space Station, and the C in CoVer stands for compact. So the objective with CoVer was to reduce the size of the radiometer system. I think polarimetric radiometers have received a lot of attention in national efforts, largely because they're seen as a way to reduce the size thanks to lower power requirements. And in a little bit, I'll get into the role that power plays in that size and cost. But we avoided them for a number of reasons. The largest is probably that they have very strict radiometric sensitivity requirements, and that really puts a higher floor on cost in terms of what optimizations you can accomplish given the existing supply chain of RF components. And then they have other limitations. The aperture typically must be larger than with scatterometers due to the fact that, or rather, because there are limitations in the ways that you can segment the footprint of that aperture on the ground in observation. And it's much more difficult, honestly requires a large aperture in any way you dice it to get a higher resolution. And then radiometers also have limitations with cloud cover and rain contamination, where the clouds and the rain provide their own microwave emission signal that can mask the signal from the ocean surface. So another instrument type that's capable of measuring winds is GNSS reflectometers. And those have been popular largely for the same benefit, which is that they're passive. While the total measurement scheme is actually more similar to scatterometry, the reflectometer itself is a receiver only. It relies on the reflection of the signals transmitted by GNSS, GPS, navigation satellite systems. And however, that comes with a limitation that your wind measurement is really best in the specular region, which is somewhat narrow. You can think of like looking at a body of water with the moon overhead, and you see the specular reflection of the moon on the water surface. So it's somewhat narrow in terms of the high quality region of data, and you can see that to some degree. So an example of reflectometers is the Cygnus satellites that were recently flown, and they're flown in a train, essentially, one that they're in a similar orbits and they follow one after the other, and that way they're able to obtain more frequent refresh measurements over cyclones. But you can see here in this image in the bottom right corner from some data from Cygnus that you typically get these line measurements that are more difficult to observe a storm well. It's harder to get the coverage you need, and with that limitation in coverage, you really have a challenge when you're looking to the future to scale your refresh for if you're considering a constellation of these satellites. That limitation in coverage really translates to a severe limitation in refresh. So the challenge with scatterometers and with all of these systems traditionally has been that their cost is very large. It's a gargantuan effort, even just to get one funded under federal funding mechanisms, and largely that's due to the cost barrier that they have to overcome and the justification. And there was this in the late 90s or early 2000s, after QuickScat was launched in 99, there was this effort, and which continued for some time, to transition from these scatterometers that were launched by NASA to an operational role in scatterometry under NOAA, and really the cost played a role in making it difficult to bring that about. So there are a number of drivers to that cost, but they all boil down, in my opinion, they all can boil down to size. When it comes to satellite launch, the size of a spacecraft creates a floor in cost for due to the requirement to pay for the launch itself. And you can innovate all you want in reducing the cost of the systems and the development, but in the end, if you don't reduce the size of the spacecraft, then your cost will still be limited by that size. So one major area of size contribution, especially with active radar systems, is that power requirement. So you need a lot of power, and that power needs to be generated on board. So that requires a lot of solar panels, a lot of surface area. But then even once you get that power, you have a problem where your RF systems are only going to be so efficient. And so you have a lot of waste heat. And fundamentally the way to dissipate waste heat, because you have no heat conduction outside of your system, and you have no convection outside of the system, or at least negligible. The way to dissipate waste heat is through radiative heat transfer, which is limited based on surface area as well. And then finally, the aperture of the antenna can be a large cost driver, even with scatterometers, where there is some segmenting that can be done to increase resolution with smaller apertures. You still have a somewhat large aperture that you need. And then other contributions to size, large component spinning and non-spinning interfaces, the need for multiple antennas if you're not spinning. So I talked about the different ways to get diverse geometry, whether it's spinning or using multiple antennas. And then if the need for propulsion systems on a spacecraft can also add a lot of size. And with those, even the supply chain decisions, all of the components that go into the spacecraft can very largely or can largely determine the size on a granular level. And then finally, there's the question of how many of each of those components do you have? Do you have within a single spacecraft itself, do you have component level redundancy, which can duplicate the number of components and increase size that way? So from our perspective, or from my personal perspective, before we even started working on this problem, before I started doing grad studies with David Long, I heard at the Small Satellite Conference, I heard a statement from an early investor in SpaceX and Planet Labs that they focus on investing in space technologies that cost 3 orders of magnitude less than the state of the art, which sounds a little bit wild, but I think he was presenting that day with some of the Planet Labs team. They presented in succession. And Planet Labs is a great example because they took optical Earth observation satellites, which traditionally were very, very large, expensive systems when you look at Landsat or other systems, and then they brought those down to the size of a shoebox or smaller. Used a lot of innovative packing techniques developed for smartphones and other terrestrial electronic systems, and adopted a really different approach. And so, we looked at this cost problem in scatterometry and formed the opinion that that cost was really driving the majority, or barring the majority of advancements, and that if we could first drive down the cost by several orders of magnitude, then we open up the potential to drive performance improvements in one area or another. And so, just a side note about our team: we're a early stage team, but we've collaborated, as I've mentioned, with David Long, who we studied with at BYU, and also with Timothy Lang at NASA, and we've started collaborating with Northrop Grumman more deeply, as they have a role in providing some of the passive systems that that the government uses, and are interested in supporting us in developing some of these active systems. So now we'll get into the system that we've arrived at and that we're working towards developing. So this is Veery, our small satellite scatterometer. It's a flat panel satellite, a meter by half a meter by 10 centimeters. That gives it it's aerodynamic, so that gives it a 2.5-year orbital life without any propulsive assistance even at a 400-kilometer altitude. It has a antenna, a fan beam antenna that runs the length, that 1 meter length of the spacecraft, and the entire spacecraft is spun. So there's no separate rotating systems. We spin the entire spacecraft, and that gives us a rotating fan beam scatterometer architecture. So in the process, that antenna generates a footprint on the ground that's 25 kilometers by 420 kilometers, and that footprint is spun circularly like a lawnmower covering the grass, and that generates a 1,200 kilometer swath. As with all scatterometers, there are different performance levels in that swath. Any scatterometer is going to have limited performance in the near swath, or at least reduced performance. That's largely due to the viewing angle. You have a less diversity of viewing angle when you're looking at the near swath, but then the mid swath and the far swath we'll get to have a much better performance. The signal that the radar uses is a 30-watt C-band LFM ICW signal, and using C-band, it's the same band that the ASCAT systems that state of the art uses, has some benefits. It's a good trade-off for reducing the weather impact of the scatterometer, so it's less affected by rain than other scatterometers at higher frequencies have been. So I want to address some of the ways we reduce by several orders of magnitude, because that is such a big objective. There are a lot of things that go into it. And one of the most important things to understand is that these different design decisions that go into cost reduction and miniaturization, they feed into each other and support each other in a way essentially that creates a positive feedback cycle. So for example, by doing this body spun nadir scanning, where we're spinning the entire spacecraft instead of having separate rotating systems, that alone reduces the size of the spacecraft. But that reduced size size and power reduces the requirement for power systems, electronics, and that mass reduction elsewhere goes back and reduces the size further required for the attitude determination control systems. So you have this positive feedback loop where if you make enough of these design decisions together, they support each other, and while they are higher in risk compared to the state of the art, they reduce the risk of each other when they're applied in tandem. So I'll address a little bit more some of the main themes in these cost reduction approaches. That flat satellite form factor is significant, plays a number of roles in cost reduction. So flat satellite form factors are an area of new and active development. Most notably, the Aerospace Corporation, in partnership with NASA and the Air Force, have a standard that they've been developing for flat satellites used on small launch vehicles like Rocket Lab or Firefly vehicles, and they call it DiskSat. And while that's not the form factor that we are planning to use, they have it provides some evidence of the capabilities that are there. And the main motivations with these flat satellite form factors are simple in that you optimize that surface area that's required for power, heat, and aperture. You optimize that with respect to the volume and mass. And so that provides you with larger solar arrays, antenna apertures, like I mentioned, potential for thermal stability. It's deeper than I'll get into today, but that larger radiative area has some potential for thermal stability, greater thermal stability than non-flat systems. And then even if the surface area provided from a flat satellite isn't enough, the deployment systems required to double or triple that surface area are much simpler, because at that point you have something of an accordion fold off of an already very large surface area. So you get even a single hinge point gets you a very large addition of surface area. But we have these other side benefits that come from the flat satellite form factor. One is that we can operate in much lower orbits, as I mentioned, due to the flat satellite aerodynamics. And those low orbits have a huge benefit for radar, because radar is a two-way operation. The path loss goes with the fourth power of the distance. So a reduction in orbital altitude of half leads to a 1/16th reduction of the path loss. And with that, you get a 1/16th reduction of requirements for power for the same signal to noise ratio. And then with that, you get some benefit in terms of increased resolution, which goes off with the square of the distance. And then finally, there's this benefit with the flat satellite form factor that you have a very large differential drag by default. And so that differential drag can be used if you're somewhat patient to move from a flat orientation with the aerodynamic orientation into a higher drag orientation, which is a demonstrated process for orbital maneuvers. And in this case, we look at it as a number of satellites deployed from a single launch could achieve the LTAN phasing required to provide more frequent refresh. So LTAN is a local time of ascending node. So it's in a sun synchronous orbit, it is the time that locally that a satellite passes over regularly. So, and then the flat satellites contribute largely to mass production. And there are other techniques that we take to support mass production. But those flat satellites support a stackability similar to what we've seen SpaceX do with their Starlink satellites, which you can see in the top right corner is a rocket cam view of the moment of Starlink deployment. They have this bar that comes off and releases the entire stack Starlink satellites. Really a phenomenal achievement on their part. And with these flat satellites, there's the potential to apply that same approach to a single rideshare slot, say a 100-kilogram rideshare slot, where we stack 10 of these satellites in that rideshare slot. And with that, we get these default meter surface areas with only something in the range of a CubeSat level cost. But with mass production, there are other decisions that are required that have to be made at the same time to support the mass production. And one of them is a risk tolerant posture. So I had talked about redundancy a little bit, but when you have a single satellite that you're launching, a one-off mission, that redundancy can be very important. If one satellite fails, one system fails, the whole mission fails. But on a constellation level, you can take a somewhat more risk tolerant posture and apply a terrestrial supply chain. So the same components that go in terrestrial applications, especially in the lower orbit that we're flying in, where the radiation environment is and the thermal environment is somewhat more tolerable. So you can apply that terrestrial supply chain, which reduces the size of the components. Been a lot of progress in miniaturization in the last decade, and also reduces their power consumption and their cost. So you drive a lot of performance just from that risk tolerant posture that lets you use newer components, and also lets you reduce the redundancy in a single system, instead focusing on your redundancy across the constellation itself. So getting into some of our performance simulations for the system, I have a comparison here between a constellation of 2 ASCATs, which is the current constellation, and a constellation of 36 of these Veerys. And the interesting thing here is this rotating fan beam architecture provides so many of these azimuth looks that the speed and direction accuracy see a very large improvement across a wider dynamic range. We're targeting a similar spatial resolution. Our plans for data downlink are still in development. It's somewhat of a solved problem, but one that we're still exploring how to do cost effectively. And then the 36 Veeries gets us 1 hour in refresh. So it gets us the hourly refresh constellation. And then the swath is almost as wide as ASCAT with all these performance characteristics. It's actually a bit wider if you include the near swath, but in this case, I've excluded it from this chart because the near swath has worse performance. And then the cost in launch, so that number there is not for a single satellite, but for the entire constellation. The cost of a single satellite is looking to be under $100,000 when we do this at scale. So when you put that into the larger constellation and add in other factors, we get to still a significantly lower cost for an entire constellation. So we've partnered with BYU quite a bit for simulations and connected with our design. So they're using our design parameters. And you can see 3 different performances here, the near, mid, and far swath. So if you ignore the blue line, which is the near swath and which we've neglected in that 950 kilometer statement of swath, you can see that the performance all the way out to 27 kilometers, which was the limit of this simulation, 27 meters per second in the speed is very good. I should have backed up and said we have the RMS speed error versus the true wind speed, and the RMS direction error versus the true wind speed. So, and again, if you look at the direction, you see the performance is very good, well under 20 degrees, all the way up to 27 meters per second in wind speed. This is a different view of that accuracy. Instead of across a range of wind speeds, this is across the swath. So the horizontal index is not as clear. That this is wind vector cell indexes. Each wind vector cell is 25 kilometers. So you can look at this as negative 600 kilometers to 0, which is nadir, to 600 kilometers. And you can see in here, you can see that reduced accuracy in the near swath, but a very, very good performance in the mid swath. And that 1.6 that I cited and 11 degrees of error that I cited above up here, those are because we're including the far swath in that metric. So, and we've done a number of simulations of the constellation coverage and refresh. The goal here is to increase refresh while decreasing cost. And I should note that there's a difference between the cost of the constellation and the size of the constellation due to launch availability. So right now, SpaceX transporter missions, which our costs are structured around, have a sun synchronous schedule and a mid inclination schedule. And so we're kind of limited to those inclinations. One of our initial studies looking at what would it take to get 3 hourly refresh was somewhat naive in terms of just looking at the raw number of hits per day and assuming we could launch into any inclination we wanted. For that one, we found that we needed about 8 satellites to get 8 hits per day. But when we look at a more realistic study where we're just using those polar satellites, and we're recognizing that hits per day is not the same as hourly refresh, we find we need quite a bit more. So the study I'll go to on the next couple slides, that one we were looking at how many hits in an hour window using just polar satellites, and we found that to get hourly coverage we needed about 36 satellites. And we have a few refinements we can still do, refinements in how we report the measurements, but also we can look into adding, supplementing some of that constellation with with not just sun synchronous orbits, but with the 45-degree inclination. So here's the results of that simulation. Anything that is blue at all got at least 1 hit. So this is Of course, a map of the world. The scale, the color scale is the number of hits, and this is the first hour window. So you can see that in that first hour, we got full coverage with 36 satellites. This one there's a gap in coverage at the bottom there, and in these diamonds near the equator. Those may be due to how we phased the constellation, so there may be some optimizations there, but almost global coverage in this hour, and then global coverage in the following hours. So 4-hour simulation in this case. And you can see the results of that simulation hour by hour here as well. So here's the first hour, number of hits versus latitude. We're above 1 in all cases. You can see that that gap in the second hour in the simulation, and then above 1 for the third and the fourth hour. So finally, I was going to address the near term and our roadmap. So we've taken a very iterative development approach. If you followed SpaceX Starship development, you may be familiar with this approach. You don't try and do everything you want to do at once, but you identify what's a minimum set of feature additions that you can test reasonably. And so we have launched a couple of very small satellites testing some of our in-house systems required to vertically integrate our satellite and achieve that flat satellite form factor. And a big benefit that we've had in this process is we've relied very heavily on testing, specifying testing requirements, both on the ground and on orbit, versus focusing on the design level requirements. So we let our engineers take responsibility for the design and design towards that test. And then the moment of truth comes when they get to that test. So our first satellite here demonstrated some very basic bus subsystems. The second one had some additional bus subsystems. And then this third one that we're launching early next year has improvement to the satellite bus, but then we're also adding a demonstration radar. This is an early photos of the radar system in development. We're wrapping up desktop testing now and working towards a mountain echo test and a high altitude balloon test to confirm the characterization of the radar. It's a very, very basic radar demonstration. So on orbit, we'll just be detecting the Earth's surface, not doing any wind measurement yet, though we may do one more similar test, another CubeSat, where we measure winds. And then this satellite will be flying in orbit in March. And as far as I can tell, should be the smallest demonstration of a radar system. Reflected signal measured off transmitted and received off of the Earth's surface in a satellite, since it'll just be a 1U CubeSat. So we have a large roadmap mapped out. We're making progress towards it. But a summarized roadmap here, I discussed that some of that first orbital tests. We have licensing for this radar satellite, which demonstrates licensing for our later satellites. And then we'll be working through this process of finishing designing the new satellites, seeking funding for the instrument development and launch, and piloting data delivery to government and private customers and other stakeholders. And one of the things I'm really excited about, as I hinted at earlier, is once we demonstrate this lower cost instrument, I think the possibilities beyond that in terms of expanded performance, whether it's higher resolution instruments, higher dynamic range, really observing the structure of cyclones much better, or whether it's companion observables, something that would be of benefit to air sea flux. I think all of those are really exciting to think about the potential there. So just wanted to note, we've received a lot of support, including a current NSF grant with BYU and Air Force contract in the past. And I'll wrap up there and go to questions.
Thank you very much, Patrick. This was great. Questions? And maybe while people are thinking of questions, I can kick things off by asking, I'm sure you said this, but what resolution you think is realistic?
We're targeting 25 kilometers as the native resolution. And then, of course, there aperture-informed reconstruction algorithms that can get you a 4x enhancement down to 6
So,
kilometers.
okay, so that was the second part of the question, that one of the excitements in existing scatterometers is the reprocessing that gets to very high resolution.
Yeah, which is possible likewise here.
Okay. And so I think that goes coupled with a question about spatial and temporal resolution sort of go hand in hand. If you have high temporal resolution, potentially you also want high spatial resolution. Has anybody done a study to assess how those two fit together for winds? Do we know?
Yeah, I'd love to see one, but I am not aware of one myself. It would be
Yeah,
great to have a line graph that says if we're targeting this temporal resolution, really goes in hand with the spatial resolution. Yeah.
that's a project for somebody on this call.
Yeah. Yeah, that would be great. Please let me know if you're working on that.
Other questions? Tony has his hand up.
Hi, Patrick. Maybe you've mentioned it. Have you made any test before going to space, airborne or putting on a tower or something like that?
Yeah, so that's where I mentioned right at the end. So again, we're in our development path. We're at the this radar test in terms of this very, very basic radar. It's not a full scatterometer instrument. That's further down here in the Veery V1.0 instrument. So right now we're doing just very basic radar testing, reflection, statistically significant detection. And that's where I was mentioning that we're within the next month and a half, we're looking at doing a mountain echo test and high altitude balloon tests. So those don't get us the over water testing that you'd need for scatterometry, but once we start getting into the full radar instrument development, then we'll go towards some airborne test.
Right. So it's the over the water test that I'm more interested in.
Yeah. And we could do that with the current payload, but we wouldn't get a lot of information because it's just it's not applying all of the scatterometer techniques in terms of post-processing. But we are close to that. So as I mentioned, we might do a before we move to the larger, that 1 meter spacecraft, we may do one very coarse scatterometer test from a CubeSat. And if we did that, then we'd be going to an airborne test of the instrument as a scatterometer much sooner.
Right. Second question. So you're using C-band. Is there any limitation or constraint for you to go to lower frequencies such as L band?
Oh yeah, the main I would love to go to lower frequencies. The main constraint is size, because you're what is that, 1/5 of the frequency, so you have to 5x your aperture. So it gets to be much more difficult from this architecture. I think it's something that will be increasingly possible as the launch environment changes. If we get satellite rideshare going off of Starship, I think we'll have some really interesting developments that enable things like that. But I'm not sure. Like once you start going to L-band, you typically see these larger deployable systems that start to be very expensive.
Right.
So
something. And the advantage of having smaller satellite is also to capture extreme UNs, right? With more frequent sampling, but the C-band has its limitation.
Right. Though there is some work in dual frequency, in cross polarization, right?
Yeah.
And cross frequency, which I think even in C-band, right? Which I think could have some potential for higher winds, and also would be more feasible from a small satellite. It would be easier for us to add another antenna on that surface than it would be to add a 5 times larger antenna.
Yeah, thank you.
Other questions? Maybe I can ask, um, I guess I'm wondering about the design of a square flat satellite rather than a circular flat satellite. It seems like in something that spins, there might be a reason to have it sort of azimuthally consistent.
We may find something along that realm. We haven't gotten quite that far down the path, but I think I suspect based on our work so far with the attitude control system, I don't anticipate a problem like that. I think the main difference between the circular and the square flat satellite designs has been designing to the launch slot. So those circular ones from aerospace are designed to take advantage of the full cross section of a small launch bearing, whereas we get more of a boxy slot that we can divide up in a SpaceX ride share.
And finally, I have one more question. You showed your pathway to development. Do you have a timeline attached to the pathway?
Oh yeah, yeah. I meant to flesh that out more, but the main limitation here is that we're looking at fundraising these next steps, the middle of the roadmap here, early next year, and the lead time for SpaceX launches is somewhat high. It's at least a year and a half, and so we're looking at a minimum time to getting to orbit. From that, the fundraising schedule and then the booking of the SpaceX launch of early 2026.
So early 2026 is
First
one
demonstration.
demonstration of the full system.
Most likely one satellite. I don't know if we'll go to that full stacking of a set of satellites initially. We might, depending on our progress in that window. But
and then presumably beyond that, it's very elastic depending on what works and what funding is available.
Yeah. I think I think beyond that, moving to scaling the constellation, I don't think the costs are as large. There's a lot of NRE, a lot of engineering development here. The development in starting to scale that constellation is somewhat different. So, and we can, as I mentioned, we can get, after we do that first demonstration, we can get 10 satellites with another single launch, as long as we've developed the capability there. So.
Cool. Well, are there any other questions? If not, we'll wrap this up for today. Thank you so much, Patrick. I'm sure people may be in touch with you with additional questions down the road.
Yeah, please do. Thank you.
This was great.
Oh, it looked like there was one more hand raised.
Maybe just applause.
Maybe dropped off. Oh, okay. Oh, I see. Yeah. Okay.